Hello and welcome to the lecture for Chapter 5, Motion in Two Dimensions. It says it's about motion in two dimensions, but it is actually about quite a few things that are going to be important, especially if you want to move on from this class and talk about how to actually solve physics problems. These are very important concepts in order to be able to solve force problems. So let's get started. So the first thing that it adds up is vector addition, where if we have a sum of vectors, then we're only going to do this graphically. We're not going to talk about how you do it analytically through numbers. But if you have a set of vectors such as A, B, and C, which are just uh, arrows pointing uh, with some magnitude in some direction. So A is a 25-meter displacement vector pointing at 49 degrees off the x-axis. And then B is 23 meters at pointing in an angle of 15 degrees off the x-axis. And C is third vector with a magnitude of 32 meters, pointing with an angle of 68 degrees below the x-axis, then all you need to do to add them together is take one of them, and then the next one, the first one goes from tail to tip. So on our diagram, we have A, B, and C added together. So the first one goes from tail to tip, and then when you add the second one, you just put the tail of the second one at the tip of the first one. So put it at this tip, and then go out from there to your new tip. And then when you add the third one, put the third one at the tail to the, or at the tip of the second, the tail of the third one at the tip of the second one, and go out a farther distance. So as you can see, these uh, all three of these are going to add together, and then they're not just going to, it's not just going to be 25 meters plus 23 meters plus 32 meters added together. You have to take into account the direction. So what actually happens is that uh, the C vector is going down so far that it basically cancels out the y, uh, the upness or the y component of the A and B vectors. So how far up they go, and you basically only end up with the x-ness or the x components of the A, B, and C vectors with a little bit of y component pointing down. So when you add them together, instead of being 23 plus 32 plus 25, which would be uh, 55 plus 25 is 80, you end up with a vector that's 50 meters long at an angle of 7 degrees below the horizontal. So vector subtraction is much the same, except instead of having a vector A, or A plus B, you take A plus negative B to find the vector A minus B. So when you look at this selection, A is going to be pointing up and to the left or up and to the right. B is pointing up and to the left. But because you're subtracting B, you take negative B. You point B in the opposite direction. You make it so that the arrow is the same length by pointing in the opposite direction. And you add these two vectors together. So just like how when you add 6 plus 6 minus 3 is the same thing as 6 plus -3. A minus B is the same thing as A plus -B. So you just flip the B vector so it's pointing in the opposite direction, and that is going to give us our final vector A minus B. Okay, just a second. There we go. So projectile motion is what we actually talk about when or is actually getting onto the point of what motion is in 2 dimensions, and it's going to be kind of the only thing that we talk about when we talk about motion in 2 dimensions. But in projectile motion, the only force acting on the projectile after launch is gravity. So for all of these points, net force is pointing down with some constant acceleration, or constant force, which means that there's a constant acceleration pointing down, and there's no force pointing in the x direction. So by Newton's second law, what this means is that there's only acceleration in the y direction and not the x direction. So all of these, so in this diagram, let me see. Yeah, so in this diagram, you are taking snapshots of it's called a motion diagram, and you are taking snapshots of a system every, say, 1 second or half a second or quarter of a second, probably closer to a quarter of a second for this one. But what you see is that since there was the only force acting on it after it leaves the cannonball leaves the cannon is or after the cannonball leaves the cannon is going to be gravity pointing straight down. As you go along the x direction, there's no acceleration. So if you plotted this out, if you remember our diagrams from a couple lectures ago, x versus t would be linear, which means that the change in x over the change in t is going to be constant no matter what. So this delta t, delta x is going to be constant over a given time period. So when we look at our motion diagrams, we look at the top line, which shows our motion in x every quarter of a second, let's say. And we'll notice that there's always the same distance between each of these diagrams, between each of these x points, because x is going to be constant. But if we showed our diagram of y versus t, it would act like a parabola, which means that the change in x, or the change in y over the change in time, so delta y and delta t, is going to get bigger the farther out you go. So delta y gets bigger the more time passes as we go in our as we look around our system, as we look in the y direction. So delta y gets bigger, but the delta x stays the same. And when we look at this together, it gives us the shape of a parabola, just like the shape that you get from just like the shape that you get when you're drawing y versus t that's the same thing as you get when you look at y versus x, or height versus distance rather than height versus time. So just a moment. So another thing to note is that projectile motion is dependent on the initial x and y velocities. So the x and y velocities come from the initial velocity and the angle that's made, or the magnitude of initial speed as it comes out of the cannon or as it comes out of your hand or whatever you're doing to throw a projectile. And this angle that you make. So if you throw something at 45 degrees versus if you throw something at 75 degrees or 15 degrees, those are all going to change the range of the projectile. So this is pretty obvious what's happening in the first diagram. You throw a bunch of projectiles at different speeds, 30 meters per second, 40 meters per second, and 50 meters per second. And they all have different ranges, or how long it takes for the whatchamacallit, for the projectile to go up and then come back down to its initial height based on what the initial speed was. What might be slightly less obvious is that as you change the angle, but you keep the same initial speed, you also change the height. So 45 degrees is going to be the longest range that you're going to see, but you also find that 15 degrees and 75 degrees are going to have the same range, even though they left off at different angles, because 15 degrees is going faster in the x direction, so it covers ground really fast, but doesn't have a chance to get as high. Whereas the 75 degrees is going really high, so it's spending a lot of time in the air, even though it isn't going faster than the 15-degree ones in the x direction. Therefore, both of these end up canceling out. And it's a fact, or it's a fun fact, that these angles, whatever you launch the projectile at, as long as you're the same distance away from 45, then it's going to have the same range. So if you're at 40 degrees and 50 degrees, so 5 degrees on either side of 45, then you're going to end up with the same range as each other. So if you try 45 degrees and you try 50 degrees, you end up at the same range as each other. So static versus kinetic friction, that was actually most of what we did for or most of what we had to do for actual motion in 2 dimensions. So I'm not entirely sure why this chapter is called that if there's so much more. But static versus kinetic friction is just different types of friction that you have available. So static friction, just a second. Static friction is just friction that will do whatever it takes to keep you. Okay, that's interesting. Static friction is friction that will do whatever it takes to keep you from moving. Whereas kinetic friction just moves points. Whereas kinetic friction just points in the opposite direction of movement and tries to stop you moving. So static friction is for when you aren't moving and you try to Stack friction is for when you're not moving and you try to move an object by pushing on it. Then what the object's going to do is, or what friction is going to do is push against you until it no longer can. So if we want to do a graph of force applied versus force of friction, then what we see is that for static friction, up until you get to a certain point, which is Fs max, stack friction is always just going to apply just enough force in the opposite direction to cancel out whatever force you're applying. But once you reach that maximum value, Fs max, it breaks down, and from that point on, it's just going to be equal to kinetic friction, which is after it reaches the maximum value that a stack friction can have before it breaks down, you'll be able to move the box, but you'll still be opposed by kinetic friction, which is some constant value. So Fs max and force of kinetic friction are both related to each other by being dependent on the normal force, which is, if you remember, the force that keeps us from falling through the floor or from falling into a wall. It's just a force that something that you make contact with makes contact back with you. So mu Sn, where mu is the coefficient of static friction, and mu Kn is mu Sn is the maximum value of static friction, and mu Kn is the constant value of kinetic friction. So both of them are dependent on this value n. It's just a difference in degrees of how much, or this value n, which is the normal force. It's just a difference in magnitude, which comes from mu s always being greater than or equal to mu k. So they have two different coefficients. But that's basically what I wanted to say about that. Just a second, let me clear my drawings. There we go. And then Hooke's law and simple harmonic motion, I believe, are the last things that we're going to do. So Hooke's law is just a mathematical relationship where the force is proportional to negative x, the negative displacement from some equilibrium position. So anything where force is equal to ma, and anything where acceleration is proportional to the negative displacement from equilibrium will follow a sinusoidal function. So what happens? So I'm not going to draw the sinusoidal function. I can, but what happens more conceptually, because this is a conceptual physics class, is that you have, say for this example where you're have a little whisk or something that obeys Hooke's law, F equals negative kx, then as you pull the whisk back, the force that's going to be pulling back is going to depend on how far out it is from its equilibrium position. So as you pull the force back, something back, then it will, when you let it go, it will start moving back towards its equilibrium position, go past with the equilibrium position where force is nothing, but there is a velocity because it's still going forward, go past it, and then start slowing down as the force wants to go back to its equilibrium position. So it starts slowing down and goes in the opposite direction, has some velocity as it passes the equilibrium position, slows down, comes back, slows down, comes back, and so on and so forth on ad infinitum. So all you need to do is understand that it goes back and forth as you draw, or as you it goes back and forth because it has a force that wants to restore itself to the equilibrium position, but restores itself a little too well. And then if you want to, if you look at x versus time, it's going to look something like this, which is just a sine wave. And that's why it's called sinusoidal displacement. So I believe that's it. Let me check real quickly. Nope. So that is going to be it. Thank you very much, and I'll see you in the next lecture. Come on.